Okay, let's keep going. And the penetrating versus non-penetrating solute. So if these molecules can go through the cell membrane, we call this penetrating molecule. And most of them in your body, actually, they belong to this category, the non-penetrating. So the penetrating solute, they will go from one side to the other side. When you reach the equilibrium, it's both sides the same concentration. So in this case, well, no effect to the volume, right? The volume does not change. But now let's look at this case. Now we put glucose. Okay, glucose, we put 2 and 4. And we know ideally, okay, well, one gonna come from here to here. They want to go because it's driven by the concentration gradient. They just want to go from the high concentration area, glucose, these 4 balls to here, and make them 3 to 3. That's what makes them happy, equal concentration. But this time, your cell membrane, this is your cell membrane. It's your cell membrane make your life difficult because cell membrane is semi-permeable. This glucose, you want to go from side 2 to side 1, follow the concentration gradient, but actually it could not because the cell membrane could not make the glucose go through. So what else can move? And the answer would be water. Water can move. So when the molecule could not go from high to low, and then water always feel like it's their job to do to go to dilute the solute. So water will go from the low solute to the high solute area. Water still go from low water to high water, but every time I say that, student got confused. So I use a different way to say water. I say water always go from the low solute, which has 2 red glucose here, to the high solute area, which has 4. So water will go to the solute to dilute the solute. And eventually the volume ratio is 1 to 2. So when we calculate the concentration, even though you have 2 glucose on side 1, 4 glucose on side 2, but the volume ratio is 1 to 2. So when we calculate the concentration, it remains the same. And that's when this movement stops. So this movement, water diffusion, in biology, we never say water diffusion. So water diffusion is osmosis. So now we reach a very important concept, osmosis. That's the water diffusion. And it still reaches equilibrium. You found there's no concentration gradient, but now the volume change based on the non-penetrable solute. So that's this case. You put the non-penetrable solute here, and the water will go from low solute to the high solute area until the concentration gradient become the same. And that's osmosis. So osmosis is water diffusion, but we never say water diffusion. We say that's osmosis. And osmosis is very important in the biological system because you change the solute, you can make the water move in or move out of the cell, and sometimes make the cell change the volume too much. You can get sick, or extreme case, you can die. The pressure to make those water move is called osmotic pressure. So apparently when you have a bigger solute concentration gradient, and you have a bigger osmotic pressure because more water gonna want to go. So let's show you the same concept. You put the solute in 2 different areas, and when the solute is impenetrable, water have to move. So water have to move from low solute to the high solute area to dilute the solute. And in the clinical field, we need to be very careful when we inject something into the patient's body. We have to consider, okay, how this solution gonna make the patient's red blood cell behave, and not just red blood cell. The water gonna go to every cells. So we have to calculate the concentration of this solution, and it's called the osmolarity. So the osmolarity definition is, it's not percentage weight, it's not molarity. These two are the units used to measure concentration. Osmolarity is just another one, the third way to measure the concentration. So you can say the percentage weight, you can say the molarity, and we add one more, it's called osmolarity. Definition, number of particles per liter of solution. And you say it's very similar to molarity. A little bit different. It's very similar to molarity. But this time we consider how many real particles. So if you add 1 mole of sodium chloride into 1 liter of water, in molarity is actually 1 m, 1 capital M, 1 big M. But in osmolarity, we consider how many particles, and we know sodium chloride put into water, it is dissolved in 2. So 1 sodium chloride, actually you have 2 particles. So it turned out is 2 OS mole, because OS mole, that's how many particles, divided by 1 liter of water. So the osmolarity would be 2 OSM, 2 OSM. So it's not mole, it's OS mole. So OS mole consider how many real particles you have. And or you can use milli OS mole. Milli is 1,000, right? 1/1,000. So we talk about this in the matrix lab. And the normal osmolarity, your body is about 300 milli OSM or 0.3 OSM. So that's the normal concentration. And you have a small wiggle room, like your body temperature, like your body pH. You have a small wiggle room. So the solution you inject into this patient's body, it need to be in this range, and we call it isotonic solution in this range. So it won't make the cell swell, won't make the cell shrink, because no water gonna move in, move out of the red blood cell and other body cell. So what's the solution? Normal saline. So in clinic, you found why there are so many normal salines. They use this to dilute all the IV medicines, because this is isotonic solution. So it's about 0.9% saline. 0.9% is you add 0.9 gram of sodium chloride into 100 gram of water. That's 0.9%. So this is the normal saline. And this, the concentration, when we do the calculation, transfer this to the mole and transfer it to the OS mole, it turned out is 300 OS mole. And that's why clinically, we don't prepare the IV solution with distilled water. We prepare them with normal saline. So that's the isotonic solution, because it gives you the normal osmolarity range. So now it brings us to the next topic, tonicity. So tonicity is how the solution make the cell behave. And we now only have 3 possibilities. When you inject a solution into the cell, into the body, patient's body, and how the red blood cell behave, it only has 3 possibilities. Either the cell swell, which means the water move in, or the cell shrink, which means the water flow out, or nothing happen, and the cell is pretty happy. So only have 3 possibilities. And this tonicity. So turn out you only have 3 possibilities. If you put clinically, we like to use red blood cell because it has the donut shape. So it helps us to visualize the shape change. And when you put the the red blood cell, when you put the red blood cell into the solution, it turns out nothing changed. You scoop the red blood cell out, it still looks like a donut. And that means no water move in, no water need to move out. So the cell is pretty happy. And we say, well, that's the same concentration. The solution, we always talk about the solution. The solution you inject into you put into the cells is the same solutions as the cell like, the same concentration. So the same we call isotonic solution. So the isotonic solution make the cell remain the same shape. A good example, 0.9% saline. We call it normal saline. That's isotonic. That's why we use the normal saline to prepare the IV solution. And if we put the red blood cell into the solution, we found, wow, the cell swell. The cell swell. Or the big word for the cell swell is called hemolysis. So sometime in the test, you will say, okay, the cells hemolyze, or Hemolyze, hemolyze, that's a verb. And that means the water move in. So the water move in because the water want to go from the outside to the inside to dilute the solute. That's why the water move in. And water free pass through the cell membrane. And in this case, we say this concentration is too low for the cell. So too low means hypo. So hypotonic solution make the cell swell. And good example, pure water. So we all know water is important. You want to drink water, but you don't know actually you can drink too much water and cause damage. It's called water poisoning. And the reason is water is a hypotonic solution. And if you put the red blood cell into the solution, it turns out the cell shrink. And the cell shrink because the water have to move from the inside out to dilute the salt. And we say this concentration is too high. And with too high, we say the hypertonic solution. So hypertonic solution make the cell shrink. And good example, salt. So people keep food 100 years ago. They keep the meat they get in the summer, and they want the meat last for long till the winter. They just cover the meat with salt, and the reason is water gonna move out. So that's the extreme hypertonic situation. And when the water move out, no bacteria can survive. That's how they keep meat for months, sometimes for years. And apparently tonicity is very important. And we do have a lady, she went to a contest. It's about 10-15 years ago when the Nintendo Wii was a pretty hot toy, and went to a contest, drink water, because they want her to drink water and hold a pee, and the winner gonna bring a shiny Wii for her kids. So turned out she won the Wii, but she drank too much water, and eventually she died because this is a hypotonic solution. So too much of her body cells swell, hemolyze, and she died. So it's called water poisoning or water intoxication. So now you know everything in your body need to be just right. Water is important. You need to drink water. But when you drink too much water too quickly, it can be dangerous. It's water poisoning. So that brings to another topic. Should you drink the seawater when you're thirsty? And we all know the answer is no, because water is a hypertonic solution. So it has too much salt. It has is close to 1,000 milliosm, so 3 times higher than your body concentration. So if you drink seawater, you actually die. You're gonna lose water, dehydrated quicker. Okay, so we finished the most difficult concept today. That's osmolarity. Let's look at filtration. Filtration is, well, you have something here, and you create a slit. Okay, the slit, and you create a pushing force. You can make the molecules go. If the molecule is smaller than the slit size, it will go through. And that's filtration. So based on the size and the pressure to push the water is called the hydrostatic pressure. Where you find it? In your kidney. So your kidney are the filter. You have two. Technically, you only need one, so you can donate one to the other. And the kidneys are the filters. They filter your blood. So the blood, every minute, 20% of your blood actually goes through your renal artery, will go to the kidney. And kidney, in AP2, you will learn that you have a lot of small tube called the nephron. And they're like small filter. You have millions of them. And when the bloods go there, they will go through the filtration process. So small molecules will be filtered out. And once they've been filtered out, if the molecule you don't want it, eventually it will end up in the urine. And important molecule, they will take them back. And this filtration process happens in the kidney. So this is the nephron. That's the nephron. This look like this tube. And in the head part, your blood go there, and the capillary bed is called the glomerulus. This is where the filtration happens because the blood keep going here, so there's a hydrostatic pressure. It's gonna push the small molecules in, and it will go through this tube. An important molecule will be taken back, but eventually those dirty particles your body don't want will go through this tube called the collecting duct, and will go to the ureter and go to the bladder. It becomes your urine. So filtration process happens in your kidney. Okay, that's it.